Thank you, Sabrina, and thank you, everyone. Thanks the organizer for inviting me to speak. I'm really sorry that I cannot be there in person. I will talk about some problems related to distance regular graphs. A more appropriate title would be problems that I don't know how to solve. I mean, and that still wouldn't be that precise because the list of things that I cannot solve is very large. So this is just a selection of things that I cannot solve. And again, I have to apologize because some of you might have seen some parts of the talk before, maybe in the Waterloo Algebraic Graph Theory seminar. And I'm running out of material. Today is International Cat Day, and I was planning to use some pictures of the cat, but I think one of the participants already spoiled those things as well. So anyway, I hope I have enough some interesting material for Monday afternoon. Okay, so I will talk about distance regular graphs, and probably by this time everybody has seen these pictures and this diagram of the distance partition from a vertex x. You have vertices at distance 1, you put them in gamma 1 of x. At distance I, you put them in gamma I of x. And we call a graph a distance regular graph if you have these constants ai, bi, ci for I between 0 and the diameter of the graph, such that for any vertices at distance d, then the x and y at distance d, the number of neighbors of y which are closer to x is ci, and the ones that are further away from x is bi. And one can show that the graph is regular of valency b0, which we denote by k, and therefore there is also an ai, which is the number of neighbors of y inside gamma I of x. Now you have the way of representing this definition in terms of matrices, and you can use the distance I matrix of gamma, where the rows and columns are the vertices of the graph, and you put the 1 in the position xy if the distance between x and y is I. And the previous relation can be written in this matrix form, and therefore from here you can get that each of these matrices ai is a polynomial of degree I in the adjacency matrix, which is the distance 1 matrix A1, and these polynomials form a sequence of orthogonal polynomials with these initial terms and this recurrence relation. Now, you probably have seen this picture. This distance partition can be written as an equitable partition. It's an equitable partition, and it has a quotient matrix, which is at the bottom of the page, and it's known that the eigenvalues of the adjacency matrix of the distance regular graph are these d+1 distinct eigenvalues of this d+1 by d+1 tri-diagonal matrix. Okay. Now, so when I put the abstract, I was quite ambitious, and then I realized when the number of slides was increasing, I thought it's better to curb my enthusiasm, and so I won't talk about matchings. There are other problems and more problems about connectivity. So I'll just talk about two things. One is about these embeddings and distortions of graphs, and a problem related to distance regular graph, and one is about connectivity of subconstituents. So for the first problem, let's say we have a graph G, and the way we think of graphs, we can embed them in on our favorite piece of paper or iPad, and we draw them by having this injective function from the vertex set to the points in this on the plane, let's say. Now, many people have done that, and in general, you can define an embedding of a graph into a Euclidean space as an injective function from the vertex space from the vertex set of the graph to that space, and you want to measure how good your embedding is, how distorted the distances in this embedding are from the distances in the graph metric, and the following definition has been. The following notion has been studied quite extensively by many people. It's called a distortion of this embedding, and is a product of expansion and contraction. And expansion measures how expanded your distances in RM are compared to the distances in the graph, and contraction the opposite, how contracted your your distances are. And the least distortion kind of takes the product of expansion and contraction. And again, that's the distortion. And the least distortion of a graph is defined as the minimum distortion over all embeddings of this quantity dist of rho. Okay, so this is defined for any graph, and I will talk about some things that we did about this parameter for distance regular graphs, some things that we could do and some things that we cannot do. Before I do that, let me give you some examples to maybe get better familiarized with this notion. So let's say this parameter, so which in case, I'm sorry if I'm going too fast. So you have this C2 of G. So you have a graph G, and C2 of G is the minimum of this distortion, dist of rho. And now I will take G. I'll give some examples. So first I will take G to be the complete graph, and try to convince you that this least distortion is 1. And so you have two directions. If you take any embedding, you have this dist of rho defined as expansion times contraction. Now in the complete graph, the distance between any vertices, x and y, so it should be there that x and y are not the same, is 1. So you have this product between the maximum of rho of x minus rho of y, the length of that, times the maximum of the inverse of that quantity, and this is always greater or equal to 1, as this calculation shows. So you get so if just producing some embedding will give you a lower producing some embedding can help you get one inequality involving this parameter. So which I didn't do, that comes at in the second part. So I guess the top part, since the C2 of Kn is the minimum of this distortion of rho over all rho, this proves that this parameter is greater or equal to 1, and there is an embedding that attains it, and is given there to embed the J vertex as this J canonical vector in Rn. Okay, so you get distortion, at least distortion 1. Now for so here, I guess it's a point of what I was trying to say earlier. So for the cubes, for example, the n-dimensional cube, Qn, here the vertices are the binary vectors of dimension n, and two adjacent if and only the Hamming distance is 1. So here we give a explicit embedding. We embed the vertex x1, xn as the vector x1, xn in Rn. And then you can calculate the expansion, and it's the maximum overall, again, x and y, which are, I should have written that they're distinct, of the distance in the Euclidean space between rho x and rho y, and the distance in the graph between x and y. But because of the definition of rho, the length of rho x minus rho y is square root of the distance in the graph between x and y. And so we get to that expression, and this we can prove that this expansion of rho is 1. And similarly, one can prove that the contraction is square root of n. And so we have an embedding with distortion square root of n. So therefore, the least distortion would be at most that much, square root of n. And then that proves one part of the inequality. For the other part, you need to argue that you cannot do any better than this square root of n. And this was done by various people, Enflow in 69, Lineal and Magen, and then Vallentin. And we'll talk about Vallentin's work in a little bit. Now, again, so I'll go back to the definition for a general graph is the minimum of this product between expansion and contraction. And these two quantities kind of go head to head. So that's the crux of the story, how to minimize this product. Now, there's an equivalent formulation, which is written here below. It's the minimum of this parameter capital D, such that the distance in the Euclidean space between rho x and rho y is bounded from below and from above by something that involves the distance in the graph between x and y, and you have this D parameter that kind of measures the how far apart these two quantities are. Now you can reformulate this part furthermore. So you can, if you have this, your embedding row, and you have these inequalities here. If you put these vectors row in a matrix, and you take the gram matrix of it, Q, then the inequalities here in the first box are equivalent to the inequalities here in the second box. If you square all the terms, you get that. The left hand side and the right hand side are clear, and it's a bit of work, but it's not too hard to see what happens in the middle, and you get this expression which involves this positive semi-definite matrix Q. And now this was used by Lineal, London, and Rabinovich, who in '95 proved that this parameter C2 of G, the square of it, equals the minimum C. I'll use a different constant here, subject to the constraint that there is some positive semi-definite matrix Q with these constraints that we saw on the previous page, that this expression in the middle is bounded from below and from above by something involving the square of the distance in the graph between x and y. Okay, and then they use this the previous result to come up with something even more useful, which is the formula at the bottom, that C2 of G, so C2, remember, it was a minimum of some quantity, and now you have it as a maximum of this quantity, where the maximum is taken over all positive semi-definite matrices Q, with the property that Q times the all one vector is the zero vector, and this parameter delta of Q is written here. It's a square root of a big fraction. On the numerator, you have things that involve pairs xy, where Q of xy is positive, and that the denominator Q of xy is negative, and it comes from this result on the top if you manipulate things in a sort. So again, so far, I give you an introduction on these distance regular graphs that you already knew, and I talked a little bit about this parameter list distortion of these embeddings of a general graph into Euclidean spaces, and I've given you some examples and some different formulations of this parameter C2 of G. Now they prove more, Lineal, London, and Rabinovich, and they show that in this formula, C2 of G equals the maximum of this expression. If you have an optimal embedding row, and Q is the matrix that comes from that and attains equality in the formula above, then what you have on the top will have terms only for the most row contracted pairs. So the pairs x and y that attain the maximum for the contraction, and the expression on the bottom will have terms only for those. So you'll have qxy is negative only for those pairs x and y, which are the most expanded pairs under your this embedding row. For one of these situation, most expanded or contracted, we know what's going on, and it's actually not too difficult to prove. And this was done by Lineal and Magen, showed that for a general embedding of a graph, the maximum of this ratio between row of x minus row of y, the length of it divided by the distance between x and y in the graph. So this expansion of row must be attained for adjacent vertices x and y, which kind of, you think, okay, kind of numerology, you have here a ratio. If I make the numerator as small as possible, maybe get lucky. That should be the, of course, that's not the proof, but the proof is here. And it uses a triangle inequality. And so we take two vertices x and y, and we look at this expression that we want to maximize. And you take a geodesic or shortest path from x to y. Now at the denominator, we have raise equality. Actually, these distances between consecutive vertices are 1, but at the numerator, it's inequality. It's a triangle inequality in whatever space we are. And then you have this, so we have this expression that we started with is at most this fraction where we have, I think, k terms on the top and k terms on the bottom. And this expression will be at most the maximum of this quantity of over rho of xi plus 1 minus rho of xi divided by the distance between xi plus 1 and xi. But that distance, this between xi plus 1 and xi is 1. So if you want a pair x and y where this is maximum, they have to be adjacent. So that's what this is trying to. So again, maybe it's helpful to think of it in this way, that the most expanded pairs x and y are going to be the ones where this denominator is the smallest, where it is 1. Again, that's not the proof, but just to help you remember it. Okay, so there are many people who have looked at these embeddings, and there's a big area in mathematics and computer science, embedding all kinds of spaces into other spaces. And so Bourgain proved that every metric space with endpoints, so every graph on endpoints, can be embedding into Euclidean space with distortion big O of log n. And this log of n is tight, and this was proved independently by Lineal, London, Rabinovich, and Matuszek. And they proved that so-called expander graphs are graphs that are attain asymptotically this log n bound. So I'll give you a sketch of a proof, and this comes from a paper by Lineal and Magen, and they prove something of this form, that if you have a k-regular graph where the second largest eigenvalue of the adjacency matrix is less than k minus, maybe I shouldn't have put epsilon, but there is a spectral gap of at least some quantity. Here, I guess we'll go with epsilon. Then this least distortion constant C2 of G is greater or equal than log n times some constant, positive constant that depends on k and epsilon. And here's a sketch of the proof. You take for any r, if you look at the ball of radius r, which is centered at some vertex, you know an upper bound for that. It's like the number of vertices in a k regular tree of depth r, and you have at most these many vertices. And now one can define an auxiliary graph from G, from the original k regular graph. So H has the same vertex set as G, and you have these two vertices in H are adjacent, if and only if they're, let's say, far apart, where far apart for us, it means distance at least log in base k of n minus 2. And now with this definition of H and with this calculation from above, one can prove that the minimum degree of this graph is large. Like for each vertex, there are many vertices which are farther away than this distance from your vertex. And so there's this theorem in graph theory by Dirac, where if you have n vertices and you have a graph and the minimum degree is at least n over 2, then you have a Hamiltonian cycle. So that's what they apply here. And the proof here is easier when n is even. So let's say n is even, and so you have a Hamiltonian cycle in this auxiliary graph H. So because you have a Hamiltonian cycle, you can pick a perfect matching from it. So essentially what you have done, you have picked up pairs, you have split the vertices of the original graph G into pairs of vertices that are far apart from each other. And we'll see this trick later on when we talk about Vallentin's results, okay? And this perfect matching, its adjacency matrix, we denote it by B. Again, to get a lower bound for this least distortion, we are going to use the result of Lineal, London, and Rabinovich, which says that the C2 of G is the minimum of this delta over all matrices Q with some property. So now we have to, one has to cook up this matrix Q. So you want Q to be positive semi-definite, and you want Q such that if the all one vector is an eigenvector corresponding to eigenvalue 0. So because A was K regular, if you take, obvious candidate Ki minus A will be positive semi-definite, and then you can afford to lose this much, so you take plus epsilon over 2 times B minus I, and you can work out that this matrix Q is a positive semi-definite, and you can work out that Q times the all one vector is 0 because it kills the Ki minus A, and it also kills B minus the identity. And so it satisfies the properties that you want, and therefore by that big hammer of linear London and Rabinovich, C2 of G is greater or equal than this expression. But now from this matrix Q, you know exactly which pairs have Q of xy positive, and you know exactly which pairs have Q of xy negative. The negative ones, you pick them up from minus A, and I mean there is an identity there as well. And then the positive ones, you pick them up from B and Ki. So once you do the calculation, and you use the definition of B, the fact that these vertices in B, are, if like you have the fact that in B you have one entry whenever the vertices are far apart, and far apart means distance bigger than log K of n minus 2. You put this in, and one gets the lower bound of log n of log n. So here the Q was again a combination of A comes from a K regular graph, so it's K identity minus A plus something else which involves these vertices which are far apart. So that is a lower bound of which matches the Burgerian log n upper bound. Oh, sorry. So in terms of least distortion of distance regular graphs, so the motivation of our work was we read this very interesting paper of Frank Vallentin from 2008, and he studied the least distortion of distance regular graphs. So he proved several interesting results. So he showed, one of them is that he showed that if you have a distance regular graph, then you can have various embeddings that give you optimal distortion, but he proved that there always exists a faithful embedding with optimal distortion. So he used this term faithful, and faithful here means that this embedding has the property that if you have two pairs of vertices x and y, and x prime and y prime, that are at the same distance in the graph, then the distance between the embeddings of these vertices will also be the same. And the way he proved that is very nice. He started with an embedding. You can take an optimal embedding if you want, and then you take Q, the gram matrix of that embedding, and you project it on this on the Bosman algebra generated by A0, A1, and AD by the distance matrices. And this projection, which you can be written in this form, one can prove that this would be the gram matrix of a faithful embedding with the same distortion as the distortion of the original embedding that you started with. So the nice thing about this result is that it allows you to think in terms of just distances in the graph when you're trying to find optimal embeddings for your distance regular. Another result that Vallentin proved is that if you take a distance regular graph with diameter d and distinct eigenvalues theta 0, theta 1, theta d, so theta 0 is the valency k, then the square of this least distortion is bounded from below by this expression. And his argument is similar in spirit to the one from the previous proof. So you want a lower bound for this parameter. So here I'm working with C2 square, so there are no square roots, just a fraction. So you want to cook up a matrix Q such that it's positive semi-definite and Q times 1 is 0. So the same as before, you take K identity minus A plus. Now he goes to the as furthest apart as you can be. So AD minus KD times identity, and this parameter alpha is picked in this way just to guarantee that the matrix is positive semi-definite. That's the point of this alpha. This way, it guarantees that it's positive semi-definite. No matter what you put here as a coefficient in front of the second bracket, you guarantee that Q times the all one vector is 0, the 0 vector. But you need this matrix to be positive semi-definite, so that's why he takes alpha this value. And then after you do the calculations, you apply again this LLR bound. You get the expression here on the top. So it's d squared vdk divided by k times alpha, which is written. Now Vallentin applied this bound to various graphs, and he proved that this bound is tight. So for Hamming graphs, Johnson graphs, and strongly regular graphs. Now for Hamming graphs, I have a notation which is a bit the two entries there are switched compared to some previous speakers. So I have here the H, Q, and N. So the length of the words is N, and the size of the alphabet is Q. So you have words of length N over an alphabet of size Q. So I write them like this, Q and N. And Johnson graph VK, vertices are K subsets of a set with the V elements, and adjacent if their intersection is size K minus 1. So he applied this bound. So Vallentin, when he applies this bound for Hamming graph, Johnson graphs, I'll show in a second little bit of the details. You can figure out these numbers, and you get a lower bound. So let me show you here. So this is for Hamming graphs. So Vallentin, there is an expression for the eigenvalues of Hamming graphs and the distance matrices of Hamming graphs involving these Krautchuk polynomials, and Vallentin proved that the lower bound, this minimum, is attained for j equals 1, and when he plugged in and did the calculation, obtained that this least distortion parameter is the least square root of n. And then, so this gives you a lower bound, and so you want a matching upper bound. And he found a matching upper bound by coming up with an embedding. So for each vertex A in the alphabet Q, EA is the characteristic vector of that singleton. And then for a vertex in the Hamming graph, which is A1 AN, he embeds this vertex in a Euclidean space which is of larger dimension, and Q, where you have EA, EA2, and EAN, each of these vectors being Q dimension. And then one can do the calculations, and using one of the other expression for this least distortion, if the distance in the graph between A and B is J, then one can work out these inequalities. And if you take the square root of everything, you get this square root of n that matches the lower bound. So that's how he did Hamming graph. So this gives also this the cubes and so on. And he did something similar for the Johnson graphs. So the definition of the Johnson graphs here in the middle box, and similar as before, these are the eigenvalues here are these Eberlein polynomials, and I think the lower bound is also attained for j equals 1. And he got this lower bound of square root of k, and then for an embedding of this distortion, he sent x to some constant times the characteristic vector of x, and then you can work out that if the distance in the graph between x and y is j, then the intersection between x and y is k minus j, and you can work out all these values, take the square roots, and you get an embedding of distortion square root of k. He also did strongly regular graphs, which I won't show you now. So he conjectured that this should work out for all distance regular graphs, that this bound his bound is tight for all distance regular graphs. And so what we did, this is joint work with one of my PhD students, Himanshu Gupta, and we started working with this with Ferdinand Ehringer. And then we obtained some results, and we talked to Jacques Coulon about it. And he remembered that Kurihara also obtained some similar results a while ago. So now we have some work on arXiv, which is joint with so Himanshu Gupta, Ferdinand Ehringer, and Hirotake Kurihara. And so we proved that his conjecture is not true. So it's true for Hamming, Johnson, and strongly regular graphs, but it's not true in general. Now, so what happens? Well, so if you look at the arguments that for the lower bound, there's nothing special in his argument about the diameter d. You can use any distance that you want r, and that's the proof. That's the result here, and that's the proof over here. And it's a similar idea to the one from the, I guess again, spirit with the one from the lineal and Mag and gave. So you have this distance regular graph. You take again a combination of k times identity minus a plus some parameter beta, the distance r, adjacency matrix minus kr times identity. And now it's guaranteed that qr times all one vector is 0, just from this definition, but you want to make this qr positive semi-definite. So you take beta, the minimum of this value for that purpose. And then when you do we apply again linear London Rabinovich bound, you get this lower bound here, which I moved it over here. So this bound here, it's the same as the one on. Okay, so then what happens? Well, started looking through some examples, and Ferdinand found graphs that for which this bound 2 that we had was better than was the bound that Vallentin did. And so the first set of examples that we found were from Hadamard graphs, and one can compute these expressions. And so from the bound of Vallentin gives that the square of the least distortion is well, I don't remember if it's the square of it's the least distortion itself. So you get this lower bound here, and we got something like this. And for mu large enough, this bound is strictly bigger than Vallentin bound, so therefore his bound cannot be tight. And then, so like I said, Ferdinand looked for other parameters, and there are other counterexamples to Vallentin's conjecture. This is again just from computations. This came up to be again the general lower bound seemed to give you better bound than Vallentin. So now, what kind of embedding? So when you look at the distance regular graphs, what kind of embedding should you think of? So we thought about using this embedding that comes from various eigenspaces. So you have, for a given eigenvalue u theta, you have this tall matrix where you put an orthonormal basis for the eigenspace of theta, and then you embed using the rows of this matrix. So the eigenvalue eigenvector equation, you can write it in terms of these rows. And so there are various properties, and you can find them in your favorite algebraic combinatorics book. And so the inner product between these vectors depends only on the distance, and one can define the cosine with respect to theta as this expression. And now these cosines have many properties, and again you can find them in various books. So they're theta eigenvector of this quotient matrix. You know exactly how many sign changes they have. Now they're called cosine in one book, and they're called standard sequence in another book. So yeah, I have to pay attention to that. But again, so these are things that are unknown. The Vallentin conjecture, actually, when you normalize by some parameters, those fractions, it boils down. It's something about this cosine sequences, and it says that for a gamma distance regular graph of diameter d, the square of this least distortion equals this this expression. Now, so his motivation when making this conjecture, and if you look at the put together the characterization of equality in that linear London-Rabinovich bound, and the matrix that he used, which was a linear this combination of ki minus adjacency matrix plus the distance d minus the valency of the distance d graph and identity, shows that he believed that for distance regular graphs. So remember from Lineal and Magen proved that the most expanded pairs of vertices are the ones that are adjacent. And so Vallentin seemed to believe that the most contracted vertices are the ones that are at distance d. And essentially what our counterexample showed is that that's not always the case. There are examples in which the most contracted pairs of vertices are the ones that are at distance diameter -1. So anyway, so his conjecture is the follows. And so we prove that that's not true in general. And then we believe that he was almost true in the sense that the most we believe that the most contracted pairs of vertices are at distance d-1 or d. But based on that, we made several conjectures. So one here, I guess, is the most general, that this C2 of G, to find it for distance regular graph, just look at distances d-1 and d, and take the maximum of these expressions. Well, the R squared you can figure out, but then you have a minimum inside here. So we tried to make sense of this maximum and minimums, and we came up with, again, like I said, a bunch of conjectures. So we have conjecture 2 is about the distances. So it tells you that if you look, so we also, and I believe that you should embed on this second largest eigenvalue. I don't have a clear reason why, but that's why θ1 is there. And in that case, we believe that this minimum is attained where d-1 or d. And then this one, the conjecture 3, is about eigenvalues. And again, it's about the θ1 being best one in some sense. So we proved that these conjecture 2 and 3 imply conjecture 1, and we check them for all intersection arrays on Brouwer's list. And then so conjecture 3 is about embedding on this θ1 eigenspace, and you can define from those the matrix U theta, you can define this embedding rho of x, and you have these parameters here just so that rho of x is rho is faithful. And conjecture 3 essentially states that this embedding is, our belief that this embedding is optimal, and C2 would be the distortion of this embedding, and so on. And we checked it for again for various parameters, for distance regular graphs with classical parameters beta greater or equal to 1 and b greater or equal to 1 and beta large, and for Taylor graphs. So okay. Oh, sorry. I think I might have. Yeah. And then sorry. And then conjecture 2, again, this is about the distances that this most contracted pair should be the one from distance d-1 and d. And we could prove that this minimum is attained in the second half of the sequence from 1 to d. And this conjecture 2 basically it gives you an upper bound on C2 of G, again, in terms of this cosine sequence of θ1. And again, we proved it for you get it that it's true for diameter 3 or 4 from this general result here, and we also proved it from classical parameters. Okay, but we don't know how to to do these things in general. So we have like some special cases. We proved that the Vallentin conjecture is not true, but yeah, we have these conjectures that we could prove only in certain situations. Okay, so this is one part of my talk. I'm sorry, I have to. So one other quick problem that I want to talk to you about is relates combinatorial properties of distance regular graphs. So strongly regular graph is a distance regular graph of diameter 2, and for strongly regular graph, it's common to use lambda for A1, mu for C2, or A for A1 and C for C2. Again, depending on which book you learn your algebraic graph theory from. Now, a graph gamma is primitive if, so I'm talking about strongly regular graph. It's primitive if the graph gamma is connected and its complement, which is the same as the distance to graph of it, is also connected. And then there is this really nice property of subconstituents in strongly regular graphs, which is that if you have a primitive strongly regular graph, then for any vertex x, gamma 2 of x is connected. And there's a very nice paper of Gardiner, Gotzel, Hensel, and Royal from '93, which gives a combinatorial proof showing that the diameter of this graph is at most 3 for any x. I won't prove that here, but there is a proof of that gamma 2 of x is connected for any vertex x in Brouwer and Hammer's book, which uses eigenvalue interlacing, and I'll try to sketch it here. So gamma 2 of x, it's a subgraph induced by vertices at distance 2 from x in a strongly regular graph, and this is a k minus mu regular graph. And if this was disconnected, then k minus mu would have multiplicity 2 as an eigenvalue for that adjacency matrix. And by Cauchy interlacing, it will lie between the two non-trivial eigenvalues of gamma. So this product, where theta 1 and theta 2 are the two non-trivial eigenvalues of gamma, this would be less or equal to 0. And once you do these calculations, amazingly, this expression factors out as k minus mu times k minus lambda minus 1. And because the graph is a primitive strongly regular graph, k beats both mu and both lambda plus 1, and this gives you a contradiction. So this is the result. Again, in summary, gamma strongly regular, gamma 2 of x is connected for any vertex x. Oh, sorry. Combinatorial proof and an algebraic proof. In 2013, it was, I think, the last geometric and algebraic combinatorics conference in Netherlands, the last GAC. Brouwer asked a question about how generalize this result to distance regular graphs. Now, I think I had all these things that I showed you before. So let me tell you what we did about this problem. So you have, again, the Bose-Meissner algebra with the distance matrices and with the primitive idempotents, E1, E0, E1, ED. And then, again, now I'll call them differently. They're dual eigenvalues, theta 1, theta 0 star, theta 1 star, theta d star, such that each idempotent is a linear combination of these matrices. And then you have that the inner product of Ex hat and Ey hat is theta h. So again, these are the cosine and the standard sequence from before. So what we proved in 2013 was that, so it's known that if you take the idempotent corresponding to theta 1, then it has one sign change. So there's one S where it goes from yeah, maybe should have put greater or equal or less or equal, but it has one sign change. And with Jacques Coulon in 2013, we proved that if you don't go all the way to, you cannot generalize the previous result by saying the last subconstituent is connected, because there are examples where that doesn't happen. And so you take union of last subconstituents. So obviously you're trying to go as far as as close to gamma d as possible. And then we prove that if S is the place where this theta j stars change sign, then this union of gamma j x is connected for any x. And we also prove that this value S has to be greater or equal to d over 2. And we did this with Perron, Frobenius, and I think eigenvalue interlacing. And we observed in all we checked all kinds of examples, and we saw that it's always the case that gamma d minus 1 union gamma d of x is connected for any primitive distance regular and any vertex x. And the box above it with s greater or equal to d over 2 implies this result is true for d equals 3 and 4, but we couldn't do it. And then later on, I visited the University of Wisconsin in Madison and told Paul Terwilliger about it. And he suggested trying to prove this for cube polynomial distance regular graphs. So I'm out of time, sorry. So essentially what we did is, this is my last slide, we proved that this property is true for cube polynomial distance regular graphs. And the key ingredient was this balance set condition that has been used in proving other combinatorial properties involving girth, for example, of cube polynomial distance regular graphs. So if you want to find out more, again, you can look up our papers, and also you can look up Paul's survey that's on arXiv. So that's it. I'm sorry for going over time. So thank you very much for your attention.
Thank you. Are there any questions for Sebi?
So Sebi, can I go first? Is okay? Okay. So Frank has this this really remarkable result that he has an optimization problem that he can prove that if there's some optimal solution lives inside the Bose-Messner algebra. Are there other optimization problems related to distance regular graphs or association schemes where that happens? And can you tell me why that optimal happens to be inside the Bose-Messner algebra, the optimal matrix?
I don't know, Bill. Yeah, that's the. Yeah, I don't know. A problem.
Yeah, I mean, it probably doesn't happen often, but there's something about it that makes the algebra work. Thanks.
So Sebi, I don't think I understood the concept of distortion. You know those graphs who are isomorphic to the one skeleton of the eigenpolytope of their second eigenvalue? Some distance regular graphs, they're isomorphic to the one skeleton of their eigenpolytope. So this would be an embedding into some sort of space. What would the distortion of this thing?
I don't know. I mean, I know that Chris has this paper characterizing. I think, is that what you mean?
Yes.
Yeah.
Yes, them.
But I don't remember. I think we checked that, but I don't remember now off the top of my head what's the distortion for those graphs.
Peterson graph is one of them.
Which ones?
Peterson.
Well, Peterson is handled by it's known for, so for strongly regular graphs, there is an expression. What Vallentin did, that worked. But
does it? And yes. If there are no more questions, let's thank Sebi again. Oh no, sorry.
So a general open question. So you mentioned that in the cube polynomial distance regular graph case, a result that the union of the second last subconstituent together with the last subconstituent was connected. Now let's consider the just the last subconstituent, which might now be disconnected. Describe the connected components. How are they? Are they distance regular in their own right, and how are they related to each other? I think that's an interesting problem.
Yeah, I don't know. I mean, I think I was looking over our paper, and I think the only example we had where the last subconstituent was disconnected were odd graphs that you had that
for example,
gamma d of gamma d of x is disconnected.
Yeah, so it might be possible to classify the cube polynomial DRGs for which the last subconstituent is disconnected. Toss that out as a possible project for anybody.
Yeah, thank you.
Now, if there are no more questions, let's thank Sebi again.